Okay. Okay. Wait. Oh, wait. One moment. Oh, I think okay, wait for a moment. Okay, while waiting. Yeah, wait for a moment. Time. I need to restart the device. Okay, now I think it's okay. All right. Okay, last discussions. We discussed about the separable method, right? Separable method. Now I would like to move on to at least go to the next sections. Linear, linear method, exact method, and so substitution method. I think three will be my main discussion for today. Hopefully three, but if not, then maybe just two. I think that's still okay. The rest will be on Monday. And at the end of the class for today, I'm planning to have just a small feedbacks review. Um, I hope it can be done, and maybe I can give you some homework, probably homework. Uh, but later I will, because the Moodle now still not available. Um, maybe it will be available after Friday, after today, maybe on Monday, maybe. Okay, now let me give you a little bit of uh, example that I haven't told you yet about the separable. There are some notes that I think is still uh, need to be think about that as well. Okay, okay, let me continue a little bit here. Okay, and then another example. Okay, I can show you. Um, if we have this differential equation and we have the conditions that is mentioned here. Now, how to solve this? Okay. Now, if you think on I think in calculus, probably I have mentioned this. This is not an elementary functions. If you derive, if you integrate, okay? If you integrate, for example, integrations e, okay, this is not an elementary function. Rather, we can more introduce this kind of integrations later when we, I think, deal with an error functions. Okay, this is actually an error function. But in calculus, we say this is not elementary, which means that we don't have um, the exact results of the integrations. Okay, so how can we solve this? Okay, that's the questions. Um, Now, if we are using the fundamental theorem of calculus, which having uh, another variable to help. Okay? Let's say we are going to have another variable. So use t as a dummy, okay? Which means to help integrate this. Okay? So if we try to integrate dy dx and integrate with respect to t, also the right side also integrate with respect to t, and let's say since we are going to use some x equal 2, let's say we are going to integrate from 2 to some x, okay? So that it makes sense that it can be done for some x, okay? So we make it as an integration function. Okay? So we are going to have yt, right? Integrate dy dx becomes yt from 2 to f, and this one is going to be just writing as it is because we are stuck on these integrations, right? And then we solve this yt, or even we input x and input 2. So we are going to have y2 is 6, right? So we are going to have 6 plus, and we just leave the integration as it is. So this is the answer. And we call this is what we call integral defined functions. Because sometimes you may have this integration as your final result. Okay, and I'm planning to give you a little bit homework for you to think, but later I will just give the link, like the Google Drive link to put your homework, and also what kind of homework you can see on that Google Drive. I will prepare a folder, and you can upload your file into that folder, at least maybe just for a few days. Okay, and next week after we a little bit completing halfway chapter 2, I'm planning to have a quiz. I will send also next week the link later, and you have several days to complete the quiz. Okay. Okay, this is just one note about the last chapter, the last section. Okay. Okay, if you have any questions, and you can just send message through the chat box. Okay. Okay, I hope you get the idea what I want to tell you about this. Okay, this is when we have some integral defined functions. Okay, that can be our solutions too. Okay, now the next one is we are going to move on to linear equations. Linear equations. Now, from what we have done last Wednesday, I hope you have idea of at least what is linear and what is non-linear. Okay? Linear means it's linear in terms of, remember, because in differential equations, we are having y as our observations, right? We observe y, which means if we have y equal function of x, then every time we have dy dx and maybe y minus x, or maybe plus a constant, then this we can tell that if there is not if there is no element that has something that make it non-linear, then we call it's linear. Unless we goes through, say that okay, we have square like that, or we have sine y. Okay, this makes non-linear. But if you have sine x, still it can be linear because it's x, not y. Okay, or maybe e with power negative y like that. It's non-linear. Okay. Or maybe let me tell you in more, for example, x squared, okay, and then y double prime plus sine x y prime. I said this is just an example. 3 and then y, okay, and then e to the x. Okay. To distinguish linear and non-linear, you just need to grouping the y, okay, only y. This is still we call linear, okay? This is linear, okay? Although you see that we have e, we have sine, but it's just for x. It's not happening in y. So we call that differential because we are talking about differentials, right? Differential equation, which means we are going to observe y, okay? If we have y equal function of x, okay? Now this we call still, this is a linear differential equation. Okay. Now we call the other part here. We call that as coefficient function. Okay. Or if we want to write in more general form, we can write in the general like an, and then let's say we have x, and then this is and like this is the power, not the power, it's the derivative, okay, the derivative, how many derivative you have, and then plus let's just directly n minus 1, okay, and then x, and then y, and then n minus 1, okay, and then plus I'm trying to include all that is possible to have, and then this is x, y prime plus a 0 y and equal b of x. This is the general formulations if you want to have all conditions for linear. Okay. We can tell these equations, okay, we call linear ordinary differential equations is, we call the term is homogeneous if, okay, this b of x equals 0. We will learn more about homogeneous later on when we learn substitutions. Okay? But for now, let's just say that this is called homogeneous if the right side, the b of x, is equal to 0. Okay. Now, the standard form, this is the general form. The standard form for the first order, okay, the standard form, the more simple than this general form. So the standard form of first order differential equations, or let me just say linear, okay, first order linear DE. Okay, let me put some line here. The standard form is y prime plus p of x y, or let me make it into different color to make it more clear. P of x y, and then equal f of x. Okay. Maybe in your textbook it's a little bit different. Okay. In your textbook it's using some another constant. Let me write your textbook versions so that you don't see any noticeable difference, but it's actually the same. Okay, it is the same. This is general form. This is the standard form. But let me focus on the standard form. Okay. And the textbook I think is the same with the standard form. Okay. This is general form. Okay. Okay. Now from this standard form, okay, this p of x, okay, if you think clearly, this is a problem, right? Let's say if we are having dy dx, if we just having just equal, let's say x, okay, or x squared, we can just integrate both sides, right? Integrate both sides, and we get the answer. Or if we think that if this part is not there, this p, if this not there, then separable method, maybe we can do that as well, right? Separable is possible if the p of x is 0, right? Now, how do we make it? How do we make it? How do we make it out?
Professor, I want to
Yes.
ask,
Mm-hmm.
p of x is a constant or is it a variable x?
It's a function of x.
Oh, okay, I understand.
Mm-hmm. So it can be x squared sine x, like I mentioned here. It can be this coefficient functions. Okay.
Got it. Thank you,
Okay.
Professor.
Okay. Now, if we are having homogeneous, for example, if the f of x is 0, let me write here. If f of x is 0, it turns out to be homogeneous. And of course, we uh, can be solved through separable, right? If you imagine the right part is 0, right? You can move the x and grouping the y, and then integrate both sides. Still can be solved, right? So homogeneous differential equation for linear can be solved through separable, but for non-homogeneous, which means we have the f functions of x, then we are having a problem here, right? Okay, now let me write in the new paper. Okay, let me write in a new paper. Okay, let me explain. I can explain here. Okay, Now this dy this dy over dx plus p of x y equal f of x. The solutions, the sum of the solutions. So let me write here the property of this. Okay, it has solution the total solution is yc plus yp. Okay. So what is yc? What is yp? Yc is solution. Let me write in the green. I think better green. It's a solution for homogeneous, and yp is solution for non-homogeneous. Okay, the total solution that might happen in our linear order. Okay. Now, if we look at so let's observe if we try to make this yc yp inside our dy dx. So d dx. So let's exchange y to yc yp. So this will be yc plus maybe make it into green. Yc plus yp plus p of x, and then exchange the y with yc yp. This will be equal to, I'm going to put a little bit to the left and make it a little bit resizing to here. Okay. Now let's just grouping all. So dyc dx plus pxyc, and then plus dyp dyp dx, right? And then plus px yp. Okay. And this is the whole thing is equal to f of x, okay, as we have in our original one. Okay. Now let's concentrate on this. Let me make it a little bit to the left. Okay. Okay, now observe that if this is homogeneous, then the total will be 0, right? The total here is 0. And if you want to observe the other one, this is actually the f of x, right? If we want to concentrate on this. Now, if we look the homogeneous, or let me just directly write the results. So we can write the or maybe just write one by one, dy dx plus pxy equals 0, and we can write this becomes dy plus p of x dx, right? We can multiply with y over dx over y, dx over y. Okay, and we can have this, and we can solve separable, right? Separable. And it gives the integrations. So and then integrations. This gives to ln y, and this will be integrations minus p of x dx, and we can have y, and let's say yc, right? That's the according to our definitions from the beginning. This will be equal to some constant from the ln, some constant e, and then with power of px dx. Okay. Or we can just write c1 y1 of x, when the y1 is e to this power. Okay. Now let's just take this aside and look on the non-homogeneous, and we can see later the results. Okay. Okay. So first, the non-homogeneous. Okay. Let's write the yp with terms another variable u, which is function of x. Okay. And when we have the y1 here, this becomes u of x, and then we have e, another e. It's the same e with the previous one. Okay, so the same idea behind. So yp, we can write yp as a c, or now is u y1. Okay. Okay, now if we take this derivative, then we will have u the y1 dx plus y1 du dx plus p of x u y1 is equal function of x. And then we grouping the some value, so d y1 dx plus p of x y1, and then plus y1 du dx equal to f of x. Now we remember that this is the homogeneous, which is 0, right? Homogeneous, okay, this one. Okay. Okay, this is 0. Then we are left with, let me continue a little bit here, that we have y1 du dx equal f of x. Now we separate these integrations, and it gives us du equal f of x over y1 of x dx. So u is integrations of f of x over y1 x dx. Okay, now remember that y1 we defined this as, well, in the previous one here, is as e with power of negative integration px dx. So we will have yp is uy1 is equal to, u is integrations f of x y1 of x dx, and y1 is e Let me put a bracket to make it clear that they separate. Okay, now let me continue a little bit. Okay, if you feel confusing, let me give you this short one later on. Okay, this is just step by step how we look into the homogeneous non-homogeneous relations. Okay, okay now why or maybe let me just continue right here. So E with power negative integrations px dx integrations of f of x, or since it's also y1 here, then we can say that this is E integrations. Now it's positive because it's I'm putting up there f of x dx. Okay, because it's before it's negative. Negative means that it's 1 over x, right? So I just changing the negative to positive, okay, for this y1 here. Okay, now y is yc plus yp as defined from the previous. So y is ce negative px dx. This is homogeneous, and then plus e okay. At least we have this relations. Okay. Okay. Now if we multiply, okay, so if we multiply with e px dx, then the one with the negative will be cancelled. So we will have e px dx y, and then c plus, this is cancelled, integrations e px dx f of x dx. Okay. And then we try to differentiate. Okay, so d dx e is equal e constant becomes 0. This will become e px dx f of x. Okay, we remove the integration. Okay, now we have these differentiations using the product rule. Okay, the product rule. So e dy dx plus p of x e, that's uh, the results, and y, and then equal e and if we divide or multiply with 1 over e px dx, okay, then this will give us back to, so we cancel all here, right? So we will get dy dx plus p of x y equal, oh, I think I missed out, this is supposed to be here, and equal to f of x. So we getting back our standard form. Okay. So what does that mean? It means that this e something here, e with power of something, it's become important, okay? Because with this e, we can solve the standard form. Okay? We can solve the standard form, and we can predict the solutions so that when we differentiate, we get back the original. Okay. Okay. If this seems a little bit confusing, let me give you maybe with a more simple way to remember. Okay. So let me give you let me give you in here. Okay. We call let me write dy dx plus p of x y equal function of x. Okay. Now the idea behind what we have in previous proving is when we multiply this, let's say let me write times some books using the terms mu of x, some other books using r, but let me just using r, it's easier to write. Okay. If we times this r with r of x, and we define this r of x as our integrating factor. Okay, we define as integrating factor. So we are going to have rx. Let me write dy dx as y prime to make it easy, and plus rx and p of x y, okay, and then rx and f of x. Okay, and then consider that if we have the rx y, if you take the derivative of this will have the results of rx y prime, right, and plus r prime x, right, and then y. Okay. Now let's see that our rxy prime is having similar structure with our equation here, right? The problem is this r prime xy is not really the same here. So let this r prime x equal with rxpx. So our idea here, our goal is to define what is our rx. Okay. So let r prime is rxpx. Okay. Now, if we try to make it this way, then we can try to separate the functions r with r and p in the other side. And we integrate this with respect to dx, integrate also with respect to dx to see what kind of relation we have. Now we have ln, right, for this r prime over r. This will be r x, right? If just imagine that if you differentiate ln, it will be 1 over r x, and the chain rule, right, r prime x, right? Okay. So that's correct, right? And then we have the right part, just keep as integrated 1, and then we have rx is actually e, right? Okay, the ln becomes e if you want to rewrite the forms. Remember, this e is similar to what I try to prove here. This is the same. Okay? So we call this the integrating factor. Okay. Now, what's next? So if we have, okay, let me just rephrase this differentiation here. So if we have d dx Rx y, and then we have Rx f of x. Okay. Now, if we take the integrations with respect to x, we can simply write y and then Rx become 1 over Rx over here. And then this one is differentiate Rx. Let me write with the green. Where Rx, or maybe what red one, Rx is e with power of integration px dx. Okay, so we can make out our solutions, that is using some kind of, we call this integrating factor. This is actually similar form from what we have in this part. Wait. Where is that part? Oh, here. It's actually similar with this one. Okay, with this. Okay, we try to make out the form, and then we integrate and make it into this one, into this. It's y equals something here, right? It's actually, we can write this y as y equal 1 over e px dx, right? And then integrations e px dx, and then f of x dx, right? Okay. But now let's just give you this short one, okay, to give you the idea more clear. Okay. Before, it's more using technical words that I don't think you will you will memorize that. Okay. Just look at this, okay, and see the idea that you need some multiplications that we call the integrating factor. Okay. Then when you try to differentiate the product using the product rule, it gives you the linear differential forms, okay, some sort of, and then you make some relations with the r prime is actually you force to be the equal to rxpx, okay, and then you find out that there must be some e with power of integrations of px dx. So that's the integrating factor. So whenever you found linear differential equations, and you can try to find out which one is p of x, then you can solve it through integrating factor. Okay, one more notes about this method. Okay, let me just give you the notes about the existence and uniqueness. That if f of x and p of x continues on interval AB, then solution exists and unique on AB. Yeah, just make sure the functions and the f and p is continuous. Okay, let me give you some examples, but let me just give you some time to maybe taking notes. I think this is the summary is this part. Okay? The previous one is giving you more idea on we have the homogeneous, non-homogeneous, and when we have the general form, the standard form, we may have two solutions, right? When the homogeneous happen and when non-homogeneous happen. And of course, from that, um, we can also relate to what we call the integrating factor. But it's actually some element that we need to multiply. And then when we try to construct the equations, we integrate, differentiate, it can be proven that it can be our solutions. So the first step is identify the p of x and find the integrating factor, multiply all with the integrating factor, and then you can solve through the integration. I will give you some examples on how to take this method. Okay.
Professor,
Yes.
do like in one question we only have one integrated factor or integrating factor, or we can have a lot like
Usually we just have one. We
okay,
just have one. Yeah.
okay, thank you.
Okay, and for the Wednesday class, I think I already give the recording, right? And I think now it's working, right? Before it's not working. I forgot to change the uh, the 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 private video to public. Okay, you can rewatch to see at least the syllabus. Okay, the syllabus, how much topics we will cover, um, and also the introductions, okay, of the differential equations, the separable method for the afternoon class, right? And hopefully, um, if we are having maybe too much topics, then I think we can skip some topics, and I believe I will just focus on the mathematics part, which means the one that use more models, maybe just slide, not really just a brief, okay, not really our focus. Okay, so our focus is just the techniques. I think that is more important, techniques and some formulations to because I think that is important for if you want to move on uh, and take some maybe advanced courses in the future. And some numerical method also I will skip. Okay, I will skip some numerical method. Okay. Okay. I think I can give you examples. Okay, how to use the integrating factor. Integrating factor. Okay. So remember that integrating factor is equations that have this e with power of integrations of px dx. So you need to find the px. Okay, what kind of functions you have to make into our integrating factor. Okay, let's go to our first example. So y prime plus, let's say 4y equal e with power of negative x. And we have the initial value of when x equals 0, y is equal 4 over 3. Okay, let me tell you the steps, and we can have, I think, two more example, or maybe just one more examples. And I think if we need to review. Maybe Monday we can have another examples, okay? Because I want to focus more on the sections first, okay? And later we can have an exercise. Okay, let me just solve this for you. Of course, from these equations, it's simply we can see that this is px, right? And this is alpha of x. Okay, and I think the first thing we need to solve whenever we have differential equation, we need to find out what kind of functions we have, what kind of relations we have. Is it separable? Is it not? Is it linear? Is it not? Okay, and then I think this is linear, right? And then we can use the integrating factor. So first, write down the integrating factor. Okay, that e. Let me just write with px dx. Now px is just 4, okay, so we can write down, or maybe let me just write e is 4 dx, and integrating 4, it's become e with 4x. Okay, and no need to plus c here. It's the constant is not really happening in integrating factor because we are going to multiply this with the with our equations. So the next step is multiply. So this is first step. Okay, first step, or step one. Step step one. Identify px from differential equations. Okay. Step two. Compute the Rx or integrating factor, and step three. Multiply differential equations with Rx. Okay, this is I think a better way to look at. So y prime multiply with the integrating factor e with power of x, and then plus 4y, and then e with power of 4x, and then equal, multiply again, and then this is e with power of negative x, right? Okay. Okay, we can clearly see if you take backward step from here, you can imagine that this is actually the product from the product rule of, if you take this, that this is e with power of 4x. Oh, sorry. This is not x4. Sorry, I forgot. Okay. E with power of 4x y. Right? Okay, if you take this as a product rule, so take the product rule, e 4x y prime plus e 4x, differentiate becomes 4e with 4x, right? 4e 4x y, and it is actually similar to what we have here. Okay, so that's true. So we can have this, and forget that we have to integrate this and also integrate this. It's e 3x, right? So this becomes e 4x y, and this will comes 1 over 3e 3x, and I will add a constant here. Okay. And then y, or actually, let me just write c1, okay? And then c over 1 over 3 e 3x plus c1 divided by e with power of 4x, or y is 1 over 3 e minus x plus c1 e 4x. And we have initial value, right, to find out what is this constant. So initial value, we have y at x equals 0 is 4 over 3. So y. So this is 4 over 3, 1 over 3 plus C1. And we got that C1 is equal to 3 over 3 is 1. So solution of DE is, or DE at oh, this is negative, sorry. Okay, and then this is the solutions. Okay. So identify the px, compute the integrating factor or Rx, or if you're familiar with other symbols like mu, you can use mu, that's fine. And multiply the differential equation with the Rx and solve. Okay, so step 4 is here. Step 4 here. Solve the differential equation with integration. So the idea, okay, we are multiplying with integrating factor so that we can have some sort of structure of the product rule. So if we can combine and having some sort of product rule from these two elements. Okay, so we need to combine this, the first and the second one here, and make it into one product rule like that. Okay. Okay, any questions here?
Professor,
Yes.
can you show us the you combine y prime e to the power 4x plus e for e to the power 4x for y, like how can it be the below one?
Okay, now this is quite a tricky one. So this is actually the essence of the method. Okay, so what we have here, let me just rephrase that. Wait, right, y prime e for x plus e for x for y. Okay, so this is what we have, right? So the method, why we call the integrating factor, is because we want to combine this into one product. Okay, and we know that this e for x and y prime, this is also e for x, and we have 4y. It seems that they are they came from the idea of the differentiating of the product rule. Okay. Now, every time you have integrating factor, is you need to combine, and you need to be able to combine what is the form before this left one, before this right one here. Okay? So we need to think backward and make it into this fg. So we need to find which one is f, which one is g, that when we differentiate, it will make this structure. Why? Why we need that? Because when we have this, if f is just y and g is another function of x, then we can integrate this and we can find the y, right? Okay, that's the idea of the integrating factor. So when we can think backwards and we know that, oh, we can know that this is coming from, this is y, this is e with power of 4x, and this is ddx. when we look at, oh, it's true that this has happened. Okay, so let me just write this first. This is what we got, and then our solution is we need to write in terms of y. So how to get our just y here? So we integrate with respect to x, so that we can remove this ddx in the front. Okay, so we will have y e for x, and then this is e 3x over 3 plus constant. That's how we get that. And so
I got it now. Thank you, Professor.
so that's why we need integrating factor, so that we can find the product, okay, the product rule. Okay, we can find the product rule structure, and then we can move backwards. Okay.
Thank you, Professor.
Okay. Okay. Any other questions? So I think for today we can just move forward, and I think no breaks for today, so we can finish early, and I can give you later, maybe at night. I will give you the homework. I will give you the link for the file, and also the how to upload. Just using the Google Drive, that will be fine. Okay, let me give you another example. Okay, so I hope you get the idea of the integrating factor. Okay. Okay. Give you another example. Okay. Solve y prime plus 2xy equal e of x minus x squared. And this is happen when you have initial conditions x equals 0, y equal negative 1. Okay, I give you a few minutes to try and check whether you are able uh, to use the integrating factor. Okay. Okay, and now I think this is if we look on the differential equation, I think we get the idea that the 2x here is our p of x, right? So we get the idea that this is p of x and this is f of x. So first is the integrating factor. So we always start with from here, and we get the 2x dx, and we get the integrations will result in e with power of x squared, right? And don't forget that no need to plus constant here because it doesn't really help, or it's useless to add constant because at the end the constant will be gone. Okay, so just write as it is, and then multiply the integrating factor to the equations. So y prime multiply with e squared plus 2xy multiply with the e x squared, or maybe let me write this first so you can see that it's x, and y, and then equal ex minus x squared, or let me write that this is like that and multiply with e x squared. So you see that it's cancelled, right? And again, we need to have some visuals or some imaginations how we can move this equation backwards to the product form. Okay? So when we differentiate, we get the product rule that has this structure. Okay? So first is look at the y prime and y. So probably it's just y, and at the other side is just y, and the other side maybe it's just e to the x squared. First we can try. So you can have some trial and error for your product here, and you can check with the product rule whether this is correct or no. So if we check, this is ex squared y prime plus ex squared. We differentiate, it's become 2x ex squared and then y. I think this is okay, right? So we know that this is the product form. And what's next? We need to find the solution for y, right? So the idea is to get the integrations with respect to the x. Now we have bx squared y equal ex, and y is ex minus x squared, right? Because it's divided by ex, or maybe write divided by let me just write c1 here, divided by ex squared plus c1. Okay, so this will be y ex minus x squared plus c1 e minus x squared, like that. And then we have our initial conditions, that is equal -1. So y is 0 plus E0 C1, and this will be equal -1. Oh, -2, sorry. So this will be C1 plus C1 -1, right? So C1 is -2, like that. Okay, now we have y ex minus x squared minus 2 e negative x squared. Okay, maybe one more example with a little bit complicated one. Or maybe later we can move back to this exercise. But I think you get the idea, right? You get the idea of the integrating factor. Okay. Okay, let me give you some notes. Okay, what might happen in or some cases. Okay, let me give you a notes here. Solve x y prime minus 4y equal x with power of 6 e to the x. Okay, let me just go straight. So first, maybe we need to simplify. So sometimes to solve the first linear order differential equation, you need to maybe rewrite the form to make it a standard form. Okay, so the idea is you need to make it as this form. Okay, so probably we are going to divide by x, so we y prime minus 4 y over x, and then x with power of 5 e to the x. Okay, I think this is already a standard form, and we know that we can take the px as -4 over x, right? Okay, let me just solve this like usual linear differential one. Okay, so we get that px is -4 over x, and f of x is x with power of 5 e to the x. Okay, and notice that p and f, they are both continuous. So p of x and f of x, they are continue on. Don't forget that we need to define the interval also, okay? Because we have this over x, so we cannot have that as 0, right? So we may have continuity from 0 to infinity. Okay, let's say that that's our idea of continuity to make it more general. Okay, so p and f is continuous. Okay, so now if we take the integrating factor, This is integrating negative 4 over x dx. So negative 4 over x, we can take this as negative 4 ln x. Okay. The x, we can take the positive, so we take this. Since x is greater than 0 from the interval, so we don't need the absolute value. Okay, so we can just use negative 4 ln x. Now we can also write the terms ln x with power of negative 4. Okay. We move with the ln form property. Okay. Now this is equal to x negative 4, like that. So we can cancel this, right? Not canceling, actually. It's a property of log. Okay, now multiply the equation with the x with power of negative 4. So we will have x negative 4 and then y prime. Let me write a little bit to the left here to make it more clear. And minus 4, this is 4, or x negative 4, and divided by x, then it's negative 5, right? And this one is 5. With 4, it becomes x. Okay. 5 minus 4 is 1, right? And look on the left side. And again, we think backwards. And how to make this happen is basically imagine if we have some product form. Okay? So probably the one is y, and the other one is probably x with negative 5. Or maybe 4, sorry. 4, because it's negatives. So we check. Okay, first we check. So first we check. So negative 4, x, negative 4, negative 1. So it's negative 5. And y. And then plus x, y prime. I think it's correct, right? So we can just use this as our product form. And this one is ex. And then we need to find y. So we integrate this with respect to the x. Then integral x ex dx. How to integrate that? So x ex. So let me just write this for you. If you want to use this, you can use it as well. Differentiate becomes 1 ex. This is just to make sure. This is 0. Oh, sorry. It's 0. This is e to the x. So it's become x ex minus ex. Okay. So we will have x ex minus e to the x plus c. So y is multiply with 1 over x minus 4. This will become x5 ex, and then this will be negative x negative 4, or 4, right? Because it's negative 4 going up become positive, and this is cx with power of 4. Okay, it seems that this is our solution. Okay. Okay. So if we look on the equations, if the lead coefficient is 1, okay, so if the lead coefficient is 1, let me rewrite in the new page, but maybe let me just let you know, take notes first. Or maybe let me write simple notes here. Okay, let me note simple notes here. So remember that at the beginning I tell you the general form. So if the general form is like this, okay, then we need to divide, right? We need to divide. So here. So divide by a1x, right? As we did before, as we did in this particular solutions. So this will be our standard form. Okay. Now, from here, as we did in our solution here, this x, okay, we need to make sure that this x is not 0, right? So the values, okay, let me write here, the values of x for a1x equals 0, this is called the singular point. It's similar to what we have in the previous singular points definitions. Okay. It makes the discontinuity. It's making the equation itself becomes undefined. So take care of the interval. Okay, another example that's particular related to the singular points. Let me give you another one. Okay. Let me give you another notes, another case. X squared minus 9, okay, dy dx plus xy is equal 0. Okay, first, this is similar case from what we have before. So we need to make sure we write in standard form. Okay, standard form. So we write dy over dx plus x over x squared minus 9 y, and this is just 0. So this is homogeneous, so f of x is 0. So we can define just p of x, that is x over x squared minus 9. And also, because we learn about the singular points, then we need to make sure that this interval also can observe in our computations. Okay? So P is continuous. So this is if we factor out, and we need to find that this should be greater 0. So we find it's +9. So this is -3 and 3. So it's negative. This is positive. So we know that this is continuity. They are continuous. Okay. We just check the continuity, then as long as x is not equal -3 and x is not equal 3, P is continuous, right? P is continuous. But, okay, to make this differential equation make sense, okay, then we need to make this value positive. Okay? So on the we can take the integration factor for this valuations. So the integration factor or the integrating factor is E. Okay. And what is this integrals? This is ln, right? This is ln. Half, right? If you feel not confident, you can try substitutions. And from this 2, we get this half. Right? And we know that this is, we can rewrite this and make it into just square root of x squared minus 9. Now, after multiplying with the integrating factor, we know that this is becoming the product form, sum of product form, right? And it seems that this is the product form. Okay. And we can check. I think I can rewrite this into directly square root. And this is equal to 0, right? If we integrate, this gives us x squared minus 9y. This is become a constant. So y is becoming c over square root of x squared minus 9. So from here, we see that either on this interval and this interval, we will have the solution. Okay, we will have this y as our solution under these two intervals. Now the problem is if we include the negative one, and it will be a trouble, right? It will be a trouble. So it's best to take the continuity to make to more the positive one. Okay. So x equal 3 and x equal -3. In this case, they are both are singular points. They are singular points because they are having discontinue at these points. And later we'll still study the singular points in the later part, but I think we're not covering in our course. Okay.
So, Professor, if we have initial value of, let's say, 3 and -3, the answer is no solution, right?
Yes.
Okay, thank you.
So you just need to think and take care of the interval. The interval. And sometimes the initial value problem is having a piecewise defined function or piecewise defined linear differential equations. Okay. Let me just give you example. Okay, give you example, and then we can move to another sections. Okay. Okay, another example. Um, dy dx plus y. Let's just say it's equal f of x, okay, just general f of x. And then initial value is y0 is equal to 0. And then f of x, it can be a piecewise. So we can also have this as our type of function. So what kind of graph is we have this is we have the functions that start from 1 here. Sorry. Start from 1 and just like that. And then the rest is from there. So from 0 to 1 is just a line, and then the rest is from 1 to infinity. It's at 0. I think that later we learn this type of graph is we call it Heaviside functions, but I'm not sure when we able to cover that as well. But let's just say we have this. Okay. Okay. Now we take the interval. Okay. So for interval from 0 to 1, we have dy dx plus y equal 1. Okay. And again, since this is an easy, p of x is just 1, so we can just take the e to the x, right? So let me just skip some parts here and you can try that as well. This will be equal to e to the x, and because from p of x1, so e with power of integration dx, it becomes e to the x, right? So exy, it's becoming e to the x. Okay, we multiply the integrating factor, and then integrations, exy, and then it's ex plus c. And this becomes y equal 1 plus ce negative x, right? And then we have the initial value that y of 0 is 0. So we must have c, or maybe you write c1, okay, to make clear. So c1 is 0, 0, so it should be 1 or negative 1 here, okay? So 0, 1, yeah, negative 1. So therefore, in this interval, the solution is 1 minus e with power of negative x. Okay. Solution at 0 to 1 interval. Or maybe let me write this to the left here. Now for x greater 1, we will have this is equal to 0 based on our piecewise defined functions. Now this will be leading to, so using the same way, this will lead us to y equal, let me just skip some part here, c2e negative x. Okay. Okay. We can now write. Okay. We can now write y is 1 minus e negative x and c2e negative x. This is for but now what we have is we still have the c2. Now c2 has a little bit of problem here because our initial value state that it should be equal 0, that it's 0. But here, the interval is not having any 0. So we need to have a different approach, okay, to make, to find out what is our constant, okay, what is our constant. So to make it continuous, okay, okay, so to make a continuous definition, we need to determine C2, okay, and make sure that it's continuous at least x equal 1, okay, at least at x equal 1. Okay. So requirement, how to make it happen is we take the limit. We take the limit as x approaching 1 from the right. So we are going to have, because it's actually like that. It's open interval. So we are going to approach this, and to make it that when we approach 1 from the right of our y of x, that x is equal 1. And it will, as implications, yes, implication, as a result, then C2e negative 1 should be equal to, okay, because we have the limit, we define that there is a limit there. So the limit on right, it should be left with this same with the left at that point, right? So we know that C2 we divide by e to negative 1 is e minus 1. And then the final solutions that we have is so this will be continuous on 0, 1. Or not 0, 1, sorry. 0, infinity. Okay. Okay, so piecewise is also a case. Okay, case. Okay. I hope you understand what I did here. Okay, so it basically say that I want to make this point here from both sides here. I want to make it continue. Okay? So continue. So we take the limit and take the limit from the right. It should be the same when the functions. So definition of continuous is the limit is equal with the functions, right? The limit is equal with the function at that point. Okay, when we approach it. Okay, one more thing before we move on. I mentioned before that we have the error functions, the so-called error functions. So the definitions, let me write just the definitions. I won't too much give you details here, but just an introductions. So error function we can write as erf of x, erf of x. This is equal to over square root of pi with the integrations from 0 to x e negative t squared dt. And we have also erfc, this is complementary of error function. 2, it's similar. The difference is this is from x to infinity of e. While we combine these two, if we plus, this is equal 1. as we know that from our improper integral in calculus, if you remember, that this, if we have this is equal 1, or 2 over square root of 5. Okay, now what the deal with these error functions is sometimes we may see some computations that we will stuck when we have this integration. So you can rewrite into the error functions if you want. So when you have any e with power of is negative x squared, t squared, we can rewrite in terms of error functions. Okay. Or if you want, you can just write as it is. Okay, no need to write error function. That's also okay. But if you want to make it more simpler, you can write into error function. So whenever you find this e with power of negative some squared, t squared, x squared in our differential equation, you can later just rewrite in terms of error function. Okay, that's the linear differential equations. Okay, if you have any questions, you can ask. And okay, I hope the big idea, okay, using the integrating factor, okay, that's the most important one. Okay, that's the one that you need to remember. The other one, if you forget, that's okay. But the integrating factor is important. Okay, so please keep in mind, okay, how to find the integrating factor. Okay, first identify the linear equation. Second, identify px. The third one, find the integrating factor. The fourth one, multiply integrating factor. Find the product form, integrate, and that's the solution for most of the cases in linear differential equation. Okay. Now the next sections, we will move to what we call the exact equations. The exact equations. This is actually related to partial derivatives. So if you still remember partial derivative, or if you maybe not familiar and maybe forget what is partial, you can take some review after this course. What is partial differential? Okay. Okay, let me move. Okay, let me move to the next one. Okay, I hope the idea uh, is fine with you. Okay, you can understand the big idea first. Okay, the next section is the exact equations. Let me write some functions for you with function of x, y. So x squared y with power of 4 plus cosine y equal 1. Okay, let me just write like this. Okay, let's differentiate and make out our own differential equations. Okay. So let me just start with some equations, and we need to structure the differential equation. So let's try to differentiate. I hope you still remember how to differentiate this. Maybe using the implicit differentiation. Okay, I hope you still remember. This is just maybe I will review also some part of calculus. Okay, how to differentiate this implicitly. Okay. Okay, first we have the left component. Okay, we try differentials. We differentiate. We have the product rule now because this is a function of x, y. Now we have 2x, y 4 plus product rule 4x squared y cubed, right? And then don't forget, if we have differentiate every y, we still need to write dy over dx. That's the rule in implicit, right? Okay. And then cosine y is also a function of y. We differentiate, it becomes sine of y dy dx. And this is equal to 0, right? Because it's just a constant. Now we can group all the dy over dx. Okay. And we have dy over dx is equal negative 2xy with power of 4 over the whole thing here, 4x squared minus y cubed. Not minus, right? Minus sine y, kind of like that. Okay, if you were given this as a question, okay, solve. Okay, we know that this answer for this different, let's say we have differential equations, this one. Can we make out our solutions? Because y itself is not isolated, right? Y is not isolated. That's the problem. We cannot separate. Okay. And I believe this not linear also, right? So what can we do to solve this? Okay. So the question is now, okay, if we given these questions, the questions next is, can we reverse the process? And solve dy dx to find y. And that is actually the big idea of our exact equations. I will just give you the context, okay? So the context here is we want to reverse this and find this, okay? Now, let me rephrase the original equation again. So x squared y 4 plus cosine y equal 1. Okay, and let this become our f of x, y, c. Okay. So function of two variables. So imagine, okay, if you still remember how to do differential or partial differential, then this, if we differentiate with partials, then this df is dou f dou x dx plus dou f dou y dy. Okay, this is the big idea. Okay, let me just give you the idea first, and then let me give you the what is the relations. Okay, Okay, now to solve the original equation here, then we first let the functions, the big F, as x squared y4 plus cosine y. Okay. Now take df. Okay, make a partial. Okay. So first, the first component we take partial x, right? Partial x. We take partial x, so we just differentiate with respect to x. Okay, so 2x y4, and cos y is just 0 because in partials we treat y as a constant. So this is dx, okay, plus we take the derivative with respect to y. So 4x squared y 3 minus sine y, and then dy. Okay, and this is equal to 0 because it's a constant, right? So let's solve this, and we make the and we may have the same conclusions. The dy over dx is okay, this is just some proving to see that implicit and moreover the partial one is more likely to get the same results, right? Okay, just to give you some introduction first. Okay, now then if we have this kind of dy dx some equation here, if we can define and make out a structure of a partials like this, okay? df partial f partial x dx partial f partial y dy. If we can make out this as our structure, then we can tailor the solution and make out the solution as the original equations. Okay. Okay. Now let's see this one. Okay. Let me move this a little bit up and this a little bit up here. This so put down there. Okay. Now this is our dou f dou x, right? This is our dou f dou y. Okay. Now let me just copy all and move to the next page to make it more clear. Okay, now from here we get the idea that dou f dou x is equal to xy power of 4, and from here that dou f dou y is 4x 4x squared y cubed minus sine y. Okay. Now, this is really interesting. Okay, so let me give more space here. Now just let's just see here. If we try to differentiate or integrate with respect to x. Well, it's technically difficult because it's actually function of two variables, x, y. So let's just say we imagine that we take the integration with respect to x like a partial one. Okay. So this f, okay, will be resulting. So we take the integration of x, so it's become x squared over 2 multiplied by 2, it's x squared. And y is just acting like a constant, but it's actually having y. And the constant is actually it's actually a function of y here. Okay, I hope you get the idea here. Okay. Now, if we bake out, okay, that this, then we differentiate one more with respect to y. Okay. We derive this with respect to y. Okay. Now dou f dou y. Okay. We know that dou f dou y is this. Okay. Now we have x squared y4. Then we differentiate y4 become 4 x squared y cubed plus f prime y. And notice that, or perhaps that we can do something here. It seems that similar, right? So probably our sine y is actually f prime y. So we set up that this is equal to 4x squared y cubed minus sine y. And let the f prime y equal negative sine y, right? So what's happened here? Then we can conclude that the f prime y is cosine y plus a constant. Let's just say C1. Okay. Now f, the big F now, since we have this x squared plus y4 and fy is cos y, we can tailor our solutions. Okay, so x squared y to the 4 plus cosine y and plus the constant 1. Or the constant is actually not really that matters, right? Or we can just say that f equal to x squared y4 plus cosine y is just a constant. Okay, it's a constant. Then I say it's constant 2. Okay, to make difference from constant 1. So we find our answer. Actually, we can find our answer. Now the big idea here, what makes the exact equation is really interesting is when we can tailor this partials. Okay, when we can define that we have something dx and something dy, then the component here we can treat that as our partials, partial of x and partial of y. Okay. Now, when we have this, how do we know that this is actually our exact equations? How do we check? Okay, how to check? Okay, now let's just say that we have that if we remember that from the beginning, the dou f dou x is, let me just write here, so dou f dou x is 2x y to the 4, dou f dou y is 4x squared y cubed minus sine y, right? Now, take the derivative, okay, partials with respect to y, and the right one is with x. Now, let me write here. So we take this with respect to y, and what we have is y becomes 8x y cubed, right? Okay, clear? And the right one is also the same, right? X is 8x y cubed. The same, right? Now when this happens, this is what we call it's exact. How to check the exactness is we check the mixed partials. Okay, remember that in the calculus we have learned that if we have f x y, if you have this, okay, so when you have this is the theorem in calculus that say that the result should be the same, or you can write partial x y is actually equal to partial y x. Okay, so when we have this and we can make sure that this is actually equal, then we say that okay, we have the exact equations. So whenever we have the m, I just write m as one component, and this is the x, and plus this is dy. This is equal to 0, and we need to check. Okay, we need to check that d dy m is equal to d dx n. Okay, then we can apply the exact equations. So this is said that this is an exact differential in some region R of xy plane if it corresponds to differential of some function. In a first order differential equation form, this is a first order. So it is exact equation if the left component or the left expressions is an exact differential. The one that we are proving. So if it is an exact differential that we are, when we check the mixed partials, then this is an exact differential. And the region R is defined by a rectangular region. Okay, let me give you a more general way to check the method. Okay, this is I just give you the idea using some functions and some formulas to give you the idea on what we are going to look for. So this is the form that we are looking for. We have some m of xy and then dx, and we have n of xy of some dy. And when we check the partials, the mixed partials, okay, so d dy m and d dx n, if they are exactly the same, then we are having this as our exact differentials, okay? exact differentials. Okay? And we may solve through this exact equations method, okay? Exact equations method. Okay. Okay, let me give you the method of the solutions, and maybe after that, if we have some time, we can have some example, or uh, yeah, maybe in the last 10 or 15 minutes, let me give you the comprehension for what we have did um, on Wednesday. Okay. Okay, let me give you the method of solutions. Okay. So given that the form is m x y dx plus n dy is equal to 0. Okay, when all the necessary definition are already in there. Okay, so there exists a function f. So exists function f of xy for which we may define this as dou f dou x. Well, the previous one I'm using the capital F is the same. Okay, the definition I will just write using the same with the textbook, so you don't get confused. Okay. So we can find the f by integrating the whole thing here for the m. So m x y dx. Okay. Now, of course, when we integrate this will result in giving you the constant, or this integration here is integration for this partial. It's giving you a constant that I previously mentioned. If we will give you a function of y. Let's say the function g. So let me write gy is the constant. We can say the constant of integrations. And then we take the integration the derivative. So we take the derivative of a partial y now. So d dy, and take the integration of m x y dx, and then the gy it becomes, let me write here, d dy gy is become g prime y. So let me write here g prime y right here. And this is supposed to be equal with the n. So the whole thing is equal to the n. Now, this gives that g prime y is n minus partial y of this. So finally, we can integrate these expressions. Okay? We can integrate these expressions and substitute the results. Okay, so we have the results here. Okay, so this result here So we integrate this part, integrate this. We integrate and substitute. Now we can write the x is the same as, let me write completely the whole thing here. This is the same as, if we take the partial x, is partial x and this is equal to, and this will be a 0. And then we can have fxy equal to n xy dy plus some function h of x. The same way, but this is the other side. This will be m xy minus. So you start from y or start from x. You will have the same method actually. So this gives you a choice. Okay, this gives you an option. Okay? And none of this should be memorized. Okay? You just need to know the partials. Okay, which one that you are going to look for. So from here, you can see that we have the integration of n and we have the integration of m. So we can choose which one that easier to be found as a solution. Okay, if you think that maybe using m, maybe the integrations is a little bit difficult to take, then you try the n. Okay, try the n, and then you will find the h of x instead of g of y. In our example at the beginning, we start finding the f or the y. Okay, where is it? Oh, here. We find f of y here. I'm using here, but it's a simple integration, and so we can solve it, right? But in the method itself, you can choose which one you are prefer. If you think m, the equation is too complicated, then start with n, and you will find the h. And h is, if you take the differentiate, if you take derivative, you will get this. Okay, which means that you take the partials. Okay, you take the partials. Oh, but perhaps this is quite confusing. So let's just say we take the example, okay, for some function, so you get more clear what happened here. Okay, what happened here. So the idea is try to play out with the partials, okay, and then take differentiation, take the integrations, and we can tailor our solution. Okay, so let's start with an example. Okay, so 2xy dx plus x squared minus 1 dy. Okay, let this and this becomes our m mxy and n xy. Okay, start we are going to be if you want to check the exactness, okay, if you want to check whether this is exact or not, then we check partial partial y for 2xy. Then we will have 2x. Okay, and check the partial x for x squared minus 1 is also 2x. So it's an exact equation. Okay, it's an exact equation. So we say that equation is exact. So from here we can take that there exists fxy when we have the dou f dou x, it will be equal to xy. And if we have dou f dou y, it will be equal to x squared minus 1. Okay, the first step. Okay, check the exactness. Now the second step, from these equations, we can rewrite the function of xy as or if we look on the 2xy and x squared minus 1, if we take the integrations, okay, I think both f of x, both partial x and partial y in this form, it's easy to be integrated. Okay, it's easy to be integrated. So if you integrate the first one, so integrate with respect to x. So this will be resulting. This will be x squared y, and don't forget that we have plus function of y. We can say f g to make it different from our f. Let's say g of y. Okay. Now we have the partial y from this f. This will be or maybe from the end. Let me rephrase this from the end. Sorry. So we take the partial. This will be x squared plus g prime y. Or maybe here. Okay. So take partials. Okay, I think that's okay. Before we conclude the results, and set this as our solution here. That provided that the g prime y is equal to -1, so g of y is -y. So as a conclusion, that our functions is x squared y minus 1. So in implicit, because we have the function as a constant, so in implicit form, this we may have x squared y minus y equal a constant. And if we want to make it, I think we can make it into explicit form. Explicit form means in y equals something. So y x squared minus 1 c. So y is c over x squared minus 1. And it define when x is not equal positive negative in 1. Okay.
Hello, Professor. I
Yes.
have a question again. If let's say we check the equation and it's not exact, it means we cannot use the exact method, right?
Yes,
We
yes,
have to
yes.
use the method.
Another method, yes, correct, correct.
Thank you, Prof.
Okay. But sometimes, maybe we can have more example that sometimes there is we call almost exact. So we can do some manipulation and make it an exact. Okay. Well, but that will be later. Okay, let me give you another example. And we can also combine the integrating factor from the previous linear differential equations with this exact equation. Okay, that's one way. Okay. So the integrating factor is having a little bit different from the previous one. But I think that will be, I think Monday I will discuss. I will just focus giving you some examples. Okay. So at least for today, the exact equations, the linear differential equations, and Monday we can continue a little bit on the exact equations, substitutions, Bernoulli equations, some study on physics phenomenon like the mechanical vibrations. Just a brief, and we can move to the second order and a higher order. I will just focus and concentrate on the uh, the mathematical concept and formulations. Okay, not really go into the numerical method. Okay, uh, I think that if we have time, we can have that as well. But I don't think we have much time for the summer course. Okay, let me give you another example. Okay, let me give you an example. Solve dy dx is negative 2x, negative y, x minus 1. Okay, first we can check whether it's exact or not, right? Or maybe before that, maybe rewrite the form first and identify m and n, right? Okay, now if we see from this differential equations, we can rewrite that it's going to be x minus 1 dy and negative 2x negative y dx, and we can make it okay. Now let this become m and this become n. Suppose that this is exact, then we can check this is and check the dx of x minus 1. This is 1, this is 1, so it's exact. It's exact equations. Now m is the x plus y, n is x minus 1. So integrating m, or maybe let me write in clear here, to x plus y, integrating with respect to x, we will have x squared, right? And then plus a function of y, right? Or I forgot the y, should be xy, and then okay. And then we differentiate this with respect to y, take the partial. So this will be x plus g prime y. And this is supposed to be equal to our n, right? So x minus 1. So g prime y is minus 1. So g of y is minus y. So take this function as x squared plus xy minus y. But we're still not done yet because we need to have our initial value. So initial value, when x is 0, y is 1. So f 0, 1 is 0 plus 0 minus 1. So the f01 is just negative 1. And now we are going to have x squared plus xy minus y equal negative 1. Okay. We can take this y, x minus 1, is minus 1 minus x squared, and we can take and make it into an explicit form. Okay, and that's the answer. Now notice that from previous, I'm just starting using the m, but actually you can try from y. If you would like, you could also try the different way. Try to solve it from y. So let's say we take the n. Okay, let's say we start from n. So x minus 1. But now we differentiate to respect with dy. So this will be taking xy minus y and then plus h of x. Okay, and then take the partial x of this. This is just to make sure that we are understand of what we are doing. Okay? So partial x is y plus h prime x, and this is equal to 2x plus y. So y is the same, so h prime x is 2x. So h of x is x squared. So it's supposed to be x squared, so f of x squared plus xy minus y, right? Same, right? So I think it's also okay. So using m, you can get the answer, and you can also get the answer. And also, you later you will see that maybe you will see that m may be easier than n, so you can just stick with m and just using this and make out in the g prime and then find out the total functions. Or if you think the n is easier, then you can start with n. But don't forget, okay, don't forget, when you take the integrations, you need to remember which part of it. If this is m, if it's m, then you take the integration with respect to dx, okay? Because m is in on the dx one, right? And if you take the n, then you need to integrating with respect to y, dy, okay? It's like you are having a partial structures and you take the integrations with respect to one respect to x, one respect to y, okay? And finally, both ways is going to have the same answers. Okay. Okay. Any questions? Okay.
Professor, after you partial derivative, like after you partial derivative, like respect to y, and you equal it to another one, right? Let's say
Yes.
you
Yes.
equal it
Yes.
in
Yes.
the end. Okay.
Mm-hmm.
Okay. Thank you.
Yeah. Basically, that's the way. Okay. That's the way. So we are playing with the structure of a partial. Okay. We integrate and we take differentiate and we take the fact that the partial xy is equal to partial yx, and this is actually the core concept of this exact equation. So it goes to be, we call it exact if it has the same exact value, okay, when we mix partials. Right? Okay. If you have any questions, if not, then I will just end up until here. We will have now a little bit of feedbacks. Okay. So I will give you some short questions, just multiple, not multiple choice, just yeah, maybe one, two, three, yeah, just 4 questions. Okay. I hope you can all join this activity. Okay, any questions so far? Uh, And as usual, you can watch the recording later on, and we will continue a little bit from the exact equation next Monday and move on to hopefully the afternoon class. We can start the higher order, okay, the higher order. And please wait for my instruction for homework and also quiz next week. Homework I will give you later tonight. Quiz maybe next Monday or Tuesday. I will send you some broadcast. If our Moodle already okay, then I will announce on Moodle. If not, then I will just go to tell one or two students to broadcast in the group, in your groups. Okay. Okay, let me stop this screen first, and let me go to my another screen. Okay, please check your screen. And this is the first comprehension. This is some sort of what we have in the wet essay class. Okay, so I just want to check whether we are understand or the basic concept. It's just a short questions, and because I think some of the question in differential equations need to be right in the long equations, then I need to prepare sometimes for preparing the questions in the online platform to make it easy for you to answer. Okay, okay, and then I think I can start with just give you. Okay, you can go to the code 3136353. You can go to menti.com. Okay, and you can use your student ID as your ID. Okay, please write your student ID. Okay. Okay, wait for other. I think we have 14 or 13, 14 students, right? Okay, I think we can start. So we can start. Okay, it's really short questions with only 20 seconds to answer. Okay, it should be quick. Okay. 6, 5, 4, 3, 2, 1. Okay, answer. Okay. Yes, it's false. Okay, it's false. Okay. It's non-linear, but it's the first order. Okay. The derivative on the first derivative. Okay. Okay, good. All right. Number 2. I'm sorry if this seems too small, but I hope you get the idea. Okay, you have the slope field and just need to check which the slope field that is on the picture. Okay, you have A, B, C, D. Then I give you, I think enough time. I hope enough time. Still 20 something. Okay, 19, 18, 17. Okay, don't panic. Okay, don't panic. Just check which one. And the easiest part is if you have the slope field, check when it's horizontal. That's the easiest one. Okay, why you guys didn't correct answer? Okay, that's okay. All right. Okay, no one get the correct answer. Question 3. Remember the stable, semi-stable, unstable, what it is. Please remember. You can check your notes if you write that on your notes. This is on autonomous differential equation, if you remember. Okay. Autonomous means there is no explicit x in the equations. It's only having y. We can say it's critical point, or the other name is equilibrium solution. Equilibrium solution. We know it's unstable or stable or semi-stable from the arrow. Okay, from the arrow. And how you get the arrow, you need to check whether it's positive or negative. Okay, it's true. Good. Okay. Question 4. Okay. Start. Okay, true or false? Is it separable or not? I hope the time is enough. Okay. Just asking separable or not asking how you can separate that, but just asking is it separable or not. Not computing, right? Not evaluating. So whenever you think that okay, because of some parts, then you can say your argument is it true or not. Okay. And careful for the sentence, it's not separable, true or false. Okay. Because sometimes maybe you may have confusion and you think that the sentence is separable. So it's not separable. Okay, 5, 4, 3. Okay. Okay, it's actually separable. Okay, it's actually separable. Okay, you can factor. You can factorize. You can factorize. Okay. Question 5. Okay, last one. Okay, which of the following is separable? Okay, I hope the time is also enough. Okay, I hope. Maybe too fast, maybe. But I do hope this is okay. Okay, 40, 39, 7. Okay. Okay, 30 seconds. Okay, 9, 8, 7, 6, 5, 4, 3. Okay. Yes, it's A. Actually, you can try to separate X and Y. Okay, last part. I need to have also feedbacks, okay? Okay, that's our comprehension feedbacks for today. So congratulations for the winner, okay? Okay. Uh, you can write feedbacks if you have, but the important one is write your student ID, okay? Your student ID. I will consider this as your attendance. Okay? Please write your student ID. If you don't have feedbacks, then just write student ID. If you have feedbacks, maybe your student ID and then what is your comments. Okay. Maybe you think not really understand for today's class. That's also okay. I can review some parts Monday. Okay. Yeah, you need to practice. So that's why maybe tonight I will inform the at least homework. Okay, homework. Which part that you need to take course. Yeah, English course is hard. Okay, if you think that's hard, then maybe watch the recording. Maybe it will help. Okay, and you can find a more way to learn. Okay, for the recording. Okay, I hope the recording can help you to understand more. Okay, if you have all filling your student ID, then this is the end of our lecture. Okay, so we are going to have another class on Monday morning and afternoon, and I hope we can finish the first order and maybe going to second order and higher order. Okay, just maybe start from the introductions and what is the difference, the idea behind it. Okay, so thank you all. Okay, I hope you enjoy my course. Okay, let me stop this screen sharing. Okay, and let me stop the recording. Okay, and see you next Monday.